Good morning, everyone. This is Mr. Couple. I'm here today with my IBSL Year 2 students, and we're going to be talking about the Earth energy balance. This is more related to the idea like how much energy is coming into the Earth and then how much energy does the Earth itself radiate? Because we talked about in our last lesson about how objects that have a temperature that they radiate energy. And so what we want to look at today is how does the energy that's coming into the Earth from the sun, how does that relate to the energy that the Earth itself is radiating outward? And this will sort of create an energy balance within the Earth. The ideal is that you want the Earth to be emitting as much energy as it's receiving so the temperature of the earth stays constant. But as you may know, because of the enhanced greenhouse effect, that we're actually raising the temperature of the earth as we dump carbon dioxide and other greenhouse gases into the atmosphere. That's actually causing the earth to retain more of the heat that it gets from the sun, and that's causing the average global temperatures to increase. So today I'm just going to be introducing this idea of the Earth energy balance and sort of this concept called the solar constant. And we'll be going through this to build up to what will be next class. We'll be talking about the enhanced greenhouse effect. Okay, let's get started. So first, I want to begin with just a review of the two equations that we learned about last time, the Wien's displacement law and the Stefan-Boltzmann equation for power emitted from a black body. This is the graph of the emission spectrum from the sun. So these are all the different wavelengths of light down here, and then the intensity of light that we receive. Usually the vertical axis on these graphs is a highly complicated number, and so I'm just going to say it's the intensity, even though it's clearly not labeled as intensity, but just realize that like it's essentially the intensity. It's like how much energy we're receiving. So what we want to do is from this, we want to be able to calculate the surface temperature of the sun. So we collect this data with our telescopes, point them at the sun. We gather this data by looking at the light that the sun is emitting, and we want to figure out what the temperature of the sun is. So any ideas on how we can do that, guys?
Would we
What's
like calculate the energy put out by the highest wavelength or the
Yeah,
highest intensity wavelength?
there you go. We want to find the lambda max. And then we know that the lambda max is going to be that constant number, which you probably don't remember. It's 2.9 times 10 negative 3 divided by did I do this right? Divided by the temperature. Wait, no, it's lambda max T equals to that. Yeah, that's what it is. It's the maximum wavelength times the temperature of the object equals to this constant value. That's Kelvin meters, I think. Kelvin meters. Yeah, there we go. So
Here,
that's yeah, Kelvin meters. um, okay, so that's what we want to do. Is from that we can figure out what the max lambda is. So I'll just look here and like drop this down. So it looks like it's at about 500 nanometers is our maximum wavelength. And then I just got to throw that into the equation and I'll be able to find the temperature at the surface of the sun. So T equals, and then we're going to use that constant number. So 2.9 times 10 to the negative 3. I'm looking at my notes over there. Kelvin meters divided by the maximum wavelength, which we just said was 500 nanometers. Nano is negative 9 meters. And then we see that the meters will cancel out and we'll just have Kelvin. And so we get that the temperature of the sun is about 5,800 Kelvin. So that's really cool. I mean, to me, I think that's cool is that we can just look at the light that the sun is giving off and we can look where the maximum wavelength is. And then from that, we can deduce how hot the sun is, at least the surface of the sun. That's pretty cool. I think that's awesome that we can just by looking at the light, like the light carries within it this information that allows us to know how hot the sun is. I mean, that's like a really interesting thing, right? Is like, how can we determine properties of the sun given that we're like 93 million miles away from it? I think it's really cool that like physics allows us just by looking at the light and like the signature of the light that we're able to figure out all these really interesting properties about not just our sun, but any star. We'll be talking more about these ideas when we study astrophysics, which will be the topic for the next 2 weeks after this. Because there's only 3 weeks left, guys, if you didn't know. Okay, next one. The sun has radius about 7 times 10 to the 8th meters. Is that 700 million meters? Calculate the total power output of the sun. Okay, so here we want power output. So we're going to need to use that other equation that we learned last class, which is the Stefan-Boltzmann equation. So the power output, that's the wrong pen. The power output by the sun is going to be the emissivity times the Stefan-Boltzmann's constant times the surface area times the temperature to the fourth power. Okay, so what we're going to do is we're going to assume that the sun is a black body. So what do you do when you have a black body? What's the emissivity constant? Do you guys remember what that is when you have a black body?
Is it 1?
It is 1. So that's saying that all of the energy is emitted from it. It doesn't retain any of its energy. The Stefan-Boltzmann constant, you can look it up in the data booklet. I'll just write it down. It's 5.67 times 10 to the negative 8th power. We're going to multiply by the surface area. So here's where it gets kind of weird. So like the sun is a sphere. So what's the surface area of a sphere? Well, we know the area of a circle, right? The area, let me draw the dotted line so you can see that it's 3D. The area of a circle is pi r squared. Well, it turns out that the area of a sphere is just 4 times that. So it's kind of cool how that works out. There's a little bit of calculus and some awesome math in there. I recommend checking out. If you just type that into YouTube, like why is the surface area of a sphere equal to 4 circles? There's this really good video that pops up from a channel called 3 Blue 1 Brown, which I highly recommend you guys check out those videos. So just remember that the surface area of a sphere is 4 times the area of a circle. So just imagine you took like 4 circles and you just like pulled it up and you'd have a sphere. So we're going to put 4 pi, and then we need to multiply by the radius squared. So it's going to be 7.0 times 10 to the 8th power, and then we need to take that squared. And I think I'm going to remove these parentheses over here just to make it look better. Okay, so now I just need to multiply all that together. This is why I have the calculator. So here you go. I actually forgot I had the calculator in the previous question. I would have done the math up there. All right, so here you go. So 5.67 times 10 to the negative 8th power times 4 pi. Don't forget to use the pi button on the calculator. So you get that more precise value of pi times 7 times 10 to the 8th power. And then I just need to square that number. The benefit of putting in the number in the calculator with this exponential notation, e, is when you put the squared there, it doesn't just apply to the 8, it applies it to 7 times 10 to the 8th. So there's the wrong answer. What did I do wrong? Oh, I forgot to multiply by the temperature to the 4th power. So I have to multiply by temperature, which we had 5,800 to the 4th power. I'm going to put that in parentheses so that I realize that it doesn't look like 58,004, but it looks like 5,800 to the 4th power. So I just need to take this multiplied by 5,800, and you need to raise that to the 4th power. And then here we have the power output from the sun. It's this incredibly large number. So this is 3.95 times 10 to the 26th, and this is in watts. So I'm going to write this. There's only 2 sig figs here because of the radius there is 7. Also, these are only 2 sig figs up there as well. So we're going to write this as 4.0 times 10 to the 26th. And then realize that's joules per second. That's what a watt is. So I just want you guys to think about this for a second. From our calculation here, which is accurate, this is an accurate calculation. The sun outputs 4 times 10 to the 26 joules of energy in a single second. For comparison, that's more energy in 1 second that the sun is releasing than humans have extracted from all energy sources in the history of this planet. The sun releases more energy in 1 second than we have extracted in all of human history. That's a bonkers notion. You guys should transmit some noises of like, wow, isn't that cool?
It's really impressive and just kind of strange how like inefficient we are at gathering any sort of solar energy, kind of
Yeah,
in light of that fact.
yeah, it is interesting. That's how much energy.
That's how much energy.
Whoa,
Whoa. We should make a Dyson Sphere.
exactly.
Alex, this is your fault.
The Dyson Sphere, right? So realize that here on Earth, we're only capturing a little bit of that energy at where we are at the distance and the size of the Earth. But if you could capture all the energy that the sun gives out in all directions everywhere, that's how much energy you'd be grabbing, and that would be what a Dyson Sphere is. So a Dyson Sphere is a proposal that you create this spherical shell around the sun, and you can grab all the energy from the sun on the surface of that sphere. Okay, so that's the idea. So what we want to do now is we want to relate that total power output of the sun. We want to talk about, well, how much of it actually makes it to the Earth? Because not all of it is. We're just a little tiny speck within this giant area of influence of the sun. So all the area around the sun is getting that 4 times 10 to the 26, but we're just going to be getting a part of it. So what we need to remember is the idea called intensity. It's been a year since we thought about intensity because we haven't talked about intensity since electricity or waves, and that was like a year ago when we learned that. All right, so we want to write down what intensity is in the mathematical equation. So intensity is defined as power per area. So power per area. So you can imagine like out here, if I want to grab what's the intensity here, I would take the power of the sun and I would divide by the area that I have there. The units of intensity are watts per square meter. So intensity is just giving you, it's taking the power and it's just spreading it out over an area. So we're saying what's the intensity of solar radiation at any given point? It's just the power divided by the area. So if we want to calculate what the intensity is at the Earth, then what we're going to need to do is we're going to need to take that power that we just calculated up above. We're going to need to take this power and we're going to need to divide it by that area of the sphere that the Earth is on. So this is a giant sphere that sort of encompasses the Earth's orbit. So imagine, the Earth is approximately going in a circle. So imagine you take the circle of the Earth's orbit and you just spherize it. And so what's happening there is that all that power, that 4 times 10 to the 26, is being spread out across this massive sphere, of which the Earth's orbit is the center of that sphere, or the like a cross section about its center. I don't know what to call that. So we define this concept. It's called the solar constant. The solar constant, and it's given the symbol capital S. The solar constant is the power per unit area from the sun. We want to determine an expression for the solar constant in terms of the distance from the sun. So obviously, as you get further and further from the sun, what's going to happen is the power is spread out over a greater and greater amount of area, which means that the intensity or the solar constant is going to drop down. So as you get further and further from the sun, the solar constant is less and less and less, which means that you're getting less and less power in the same amount of area. So if you think about like solar panels, they say that solar panels don't work on spacecraft beyond about Jupiter. So if you want to go past Jupiter, solar panels aren't going to work because the intensity, the solar constant, gets so small at those large distances from the sun that it's just not gathering enough power to chart or to run the equipment on the spacecraft. So then you need to switch to other options like maybe a thermonuclear radioisotope generator. I think that's what it's called, like a RTG or something like that. Is that what it's called? Anyway, if you guys watch The Martian, there's a really good scene with the RTG in there. But yeah, that's how we do missions to further planets is you use nuclear power. Okay, let's see. All right, so what we want to do now is just calculate the solar constant. So S is going to be equal to the intensity. I'll just put that there because we're defining that as the solar constant. We're defining it as the intensity of the solar radiation. So that's just going to be the power divided by the area. And then that area is going to be the area of the sphere. So I'll just write down sphere right there. So we know the power is going to be P. We calculate the P up above with that number 4 times 10 to the 26. And then the area of a sphere is just 4 pi. And we'll put D squared in there, where D is just how far away you are from the planet. So in this case, the radius of the orbit, that would be like our D. So D is how far you are from the sun. And then you can calculate the solar constant with this equation based on how far you are from the sun. And so once again, you can see that as you get further away from the star, as your distance from the star increases, your solar constant is going to decrease. The average orbital distance of the Earth is 1.5 times 10 to the 11 meters. Above the atmosphere, the solar constant is about 1400. So we're going to try to ignore the atmospheric effects today because it's just going to make everything more complicated. We'll deal with the atmosphere next time. So at the top of the Earth's atmosphere, you get this solar constant of about 1400 watts per square meter. Based on that observation, so we gather this much we measure this intensity of light at the atmosphere of the Earth. Well, then what's the power output of the sun? We should be able to work backwards. Okay, so here's the idea. So we're going to use this equation that we just derived. We're going to use S equals to P over 4 pi d squared. But we're going to solve for P. So P is going to equal 4 pi S d squared. And we should be able to get the same power value that we got earlier with this same expression. So 4 pi, and then for S, that's the intensity, it's 1400 watts per square meter. And we're going to multiply that by the distance between the sun and the earth, which is 1.5 times 10 to the 11 meters. And then we need to square that since it's a surface area. So let's go ahead and punch those in the calculator. So I'll do 4 pi times 1400 times the distance to the between the sun and the earth, 1.5 times 10 to the 11. And then I just need to square that. And then we get the same number, 4 times 10 to the 26. Four point zero times 10 to the 26 watts. All right, I guess in retrospect, it would have been better to find that number, that solar constant value, but yeah, I just thought it'd be cooler to show you that this actually works out. So we are able to get the same power with that value. And the reason is because that's the thing. The reason I did it this way was because that's the thing we actually measure. So we actually measure the solar constant. We measure the intensity of sunlight that reaches the Earth. And then from that, we can trace back and figure out the power output from the sun. It matches with the other way of looking at it. When you look at the peak wavelength where the intensity is at its maximum, at what wavelength, and then you do it that way too. So they're consistent with each other. Okay, here's the thing though. Like not all the light that hits the earth, like looking at this picture, not all the light from the sun that's coming in, not all the radiation actually makes it to the earth because some of it actually gets scattered. Like some of it actually reflects off the earth. And so we need some way of expressing that, like how much of the incident power actually gets scattered off the earth. And the way you do that is with a constant called albedo. And maybe some of you guys learned about albedo when we were studying for the group 4 project. So albedo, the symbol is alpha, Greek letter for alpha, is defined as the ratio of the power of radiation scattered from the body to the total power incident on the body. Therefore, we can think of albedo as the reflectivity of an object. All right, so to define albedo, what we say is the albedo is, and so it's a ratio of the power of the radiation scattered. So it's the power scattered divided by the power incident. Okay, so here's a question. Which has a higher albedo, snow or charcoal? Which one's going to have a higher albedo? Which one's going to have a higher reflectivity, snow or charcoal?
Snow.
Yeah, why?
Because it reflects sunlight more, and black absorbs a lot of sunlight.
Yeah, there you go. So we can say that charcoal is black, so it absorbs light, whereas snow reflects light. So that's why snow is a higher albedo. I wish I knew the numbers off the top of my head. I don't. I should have prepared that, but charcoal's albedo could be like really low, like 5 or 0.05, whereas snow could be like 0.8. So just depending upon what type of material the light's going to hit, it's either going to get absorbed by the material or it's going to get scattered or reflected, bounce off the material. And so snow has a lot higher albedo than charcoal does. So imagine like when you're like during the winter time, if there's a layer of snow above some ice, that ice won't melt as easily in sunlight. So like think about I'm trying to think about like just think about how when the snow gets packed on the ground, like it just stays there, even though it's like really hot outside. Like the snow, not all the snow melts, and that's because like the snow, the layer on top can actually insulate the snow underneath it, and then when the sunlight comes in to try to melt all the snow, a lot of that sunlight actually just reflects off it. So not all the snow is gonna melt, even when it's like above melting outside. So it's almost like that snow acts like as an insulation layer. I don't know if that's a good example, but snow has a high albedo, charcoal has a low albedo. So albedo is the reflectivity. So like it's the higher albedo is, and albedo is always going to range between 0 and 1. So albedo is going to range between 0 and 1. So 0 where it means like none of the light gets reflected, and then 1 which means all the light gets reflected. So this is a good question. What's the albedo of a black body?
1. I mean 0.
So black body albedo equals to 0. Yep. So the black body doesn't reflect any light. That's what makes a black body, is that none of the light gets scattered off of it. All of it gets absorbed. Good job, Kelvin.
Well, the stream froze for.
You want me to try resetting it? I'm gonna reset it. Okay, hopefully it's working now. Is it?
Yep.
Okay, cool. Okay, so what we want to do now is we want to look at the energy balance of the Earth. So we want to look at like how much energy is coming into the Earth versus how much energy is the Earth itself emitting. So the solar radiation that reaches the Earth, it goes through the area of a disk. And so that's what you're seeing in this picture here. So imagine this is a disk, and then here's your energy from the sun coming in. So the sunlight is coming in this way, and it's going to all have to pass through that disk. And that disk, notice, is exactly the same as the diameter of the Earth. So that disk has radius equal to the radius of the Earth, where that radius of the disk is equal to the radius of the Earth. So all the light that hits the surface of the Earth passes through that disk. So we could say that the power through that disk is just s pi r squared. And so that's what we're doing here is we're taking the area of the disk, the area of the disk, and we're multiplying it by s, where s is the intensity. This is just coming from this equation up here. So if we solve this equation, this part right there, if you solve that for P, you get area times solar constant. So we can say that the power that goes through the disk, the power that's incident on the Earth, is just S, the solar constant, the 1400, times pi r squared, where the area is the area of that disk. Now realize that the area, the actual surface area is going to be different than that. But like I said, we're going to be ignoring the surface effects. We're just looking at the atmosphere. All right, so show that the power of radiation absorbed by the Earth is equal to this expression right here. And we're like, okay, that expression looks crazy. Okay, so here's what we know. We want to show that the radiation absorbed. So the power that gets absorbed, so the power absorbed is going to be equal to the power incident minus the power scattered. So not all this power is actually going to get absorbed into the Earth, because some of it will actually get reflected back. You know, like if it hits water, the light's going to bounce off the water. Or if it hits ice, it's going to bounce off the ice. But what if it hits like dark soil? Well, then it'll get absorbed. So not all of the light is going to get absorbed to the Earth. So we want to figure out what is the power of light being absorbed by the Earth. And that will be like, that's the energy that stays on the Earth. The rest of it gets reflected back into space. All right, so to find the power absorbed, I'm just going to call it P now. We need to take the power incident, which we have S pi r squared, minus the amount that gets scattered. We'll realize that the scattered amount is going to be the albedo of the Earth, the reflectivity of the Earth. This is the percentage of light that gets reflected times S pi r squared. So S pi r squared is the amount that we're getting incident on the Earth, and then a certain percentage of that is going to get scattered off the Earth. So we just have to take the incident minus the percent that gets scattered. And then you get this, and then you can see that if you just factor out the S pi r squared, we get the expression up above. 1 minus alpha S pi r squared. So that's the power absorbed by the Earth, and we have to take into account the albedo of the Earth. So notice if the albedo were 0, if the Earth were a black body, then all of the power would be absorbed. But as the reflectivity increases, so like what if the Earth were a mirror? Well, then the albedo would be 1, and then 1 minus 1 would be 0, which means that no power would be absorbed because all the power, all the light bounces off the Earth. Question B, the solar constant at Earth is 1400 watts per square meter, and the Earth has a global average albedo of 0.35. calculate the average intensity of sunlight that reaches the Earth. So this is the question I was telling you guys about that I had a typo on. So this is the correct question, how it should have been written. Okay, so let's do this. So we want to find intensity. So intensity is power divided by area. Okay, check my notes, make sure I'm doing this right. Yep. Okay, and then we know what the power is. It's 1 minus alpha s pi r squared. So that's the amount of power that gets absorbed by the Earth. And then we're going to divide that by the area of the Earth. And the area of the Earth is 4 pi r squared, because we're just looking at the surface area of the Earth. So we'll notice what happens is that the r squareds cancel out, the pi's cancel out, and we just get 1 minus alpha times the solar constant divided by 4. So basically, only 1/4 of the intensity is 1/4 as much of this thing here. All right, let's just figure this out. So we're going to take the albedo of the Earth, which is 1 minus 0.35, so the albedo is 0.35. The solar constant was 1400. We're going to take 1/4 of that. And so that gives us the intensity at the ground, at the surface of the Earth. And this is ignoring, like I said earlier, this is ignoring atmospheric effects. But let's do this. Okay, so we're going to take 1 minus, come on, turn on calculator. 1 minus 0.35. I'm going to multiply that by 1400 and then divide that by 4. And so we get about 230. And then you may recognize this number from a previous lesson when we were talking about solar power. This is the number that I used to calculate the energy output of a solar panel, that we assume this is like the average intensity of light that reaches the Earth. And then you could put that in to figure out, well, what size solar panel would we need to generate this much power? Okay, now let's get to the meat of the lesson, since we're winding up here. How much time do I have left? I got like 3 minutes. Oh, this video is going to go over. Okay, so let's talk about the Earth energy balance. So to determine the energy balance of the Earth, we must compare the amount of solar radiation that is absorbed by the Earth to the amount of radiation emitted, not reflected, but emitted, because the Earth acts like a black body, and since it has a temperature, it's going to be emitting power, just like any object that has a temperature emits power. So we want to look at how does the energy coming in relate to the energy the Earth is emitting. State the effect the following energy balances will have on the average global Earth temperature. Okay, so what happens if the Earth absorbs more energy than it emits? What's going to happen to the Earth's temperature if it absorbs more energy than it emits?
The temperature will increase.
Yep. Temp goes up. Okay, what if we absorb less than we emit?
The temperature decreases.
Temperature goes down. And so what if the amount of energy that the Earth absorbs is equal to the amount of energy that it's emitting?
Temperature stays constant.
Yep, and we're going to have constant temperature. Okay, so here's what we're going to do. Based on all the math we did today, we're going to pull it all together. We're going to answer this question. The Earth has a global average albedo of 0.35 and emissivity of 0.8. So it's not quite a black body. Calculate the constant Earth temperature. Okay, so what we're going to do is we're going to take the Stefan-Boltzmann power, which was E sigma A T to the 4th power. That's the power emitted by the Earth, but based on the Earth's temperature, it's going to emit power. And we're going to say that that's going to be equal to the absorbed energy that we calculated up here, this one. 1 minus albedo times S pi r squared. 1 minus albedo times S pi r squared. Okay, and so what we want to do is we want to calculate the constant temperature of the Earth. So if the power the Earth emits is in balance with the power the Earth absorbs, then the temperature should be constant. So let's calculate what that constant temperature is. And this will tell us the average temperature of the Earth. Okay, let's do this. So next line, I'm going to realize that the area is the surface area of the Earth, which we already know is 4 pi r squared. And if we do that, we can see that the pi and the r squareds will cancel out. Okay, now I want to find what t is. So t to the 4th power is going to be equal to 1 minus alpha S divided by E sigma. I just ran out of time.
Keep going.
I'll just keep going. All right, so then, okay, so now I'm just going to have to take so to find the actual temperature, I'm going to have to raise this to the 1/4 power. Well, I guess I'll just put it over here. I'm going to raise both sides to the 1/4 power. And then that will let me find what T is equal to. Okay, let's calculate it. So let's start plugging in. Okay, so we're going to do 1 minus the albedo. The Earth's albedo was 0.35. I think that's right. Yep. Times the solar constant, which was 1400. Then we're going to divide by the emissivity of the Earth, which was 0.8, times the Stefan-Boltzmann constant, which is 5. You'd look this up in a data booklet. 5.67 times 10 to the negative 8th power. Okay, let's see. And then I'm going to take that, and I'm going to raise that to the 1/4 power, or take the 4th root of it. And then I get that answer, 376. I feel like this is wrong. Yeah, I forgot a 4 somewhere. I forgot this 4 right here. That 4 goes down here. Okay, let's see how I can fix that. Second, enter, second, enter. So I need to insert a 4 times right here. Ugh, what did I do? 4 times 0.8. So this needs to be, I lost the decimal point there. 4 times 0.8 times, yeah, there we go. And then that is going to be to the 1/4 power. There we go. That's what I was looking for. 266. Let's do it. We only have 2 sig figs, so we'll say 260 Kelvin. Okay, now what is that in Celsius? What is that in Celsius? So to convert from Kelvin to Celsius, what do you do?
-7 degrees Celsius.
Yeah, you minus 273. So that's -7 degrees Celsius. It says comment on this result. So this says that the average Earth's temperature is below freezing. Is that correct?
Hades, no.
No. So then what does that mean? The Earth is hotter than this. Why? What are
Because of
we?
the atmospheric effects you were talking about earlier.
Exactly right. So in this part here, I'm going to have you guys do this just as your last assignment for today. You need to comment on this result. So we're going to say something like, "Hey, this is way colder than the Earth actually is. If the Earth had no atmosphere, we would be a frozen ball at the distance we are from the sun. So the distance we are from the sun, that's what gives us this S value of 1400. Based on our distance that we are from the sun, the planet should be a frozen ball of ice. Like we should be -7 degrees Celsius average temperature, but we're not. And the reason is because we actually have an atmosphere around the Earth. So if we think about this picture here, there's actually an atmosphere around the Earth. And so what happens is when the Earth goes to radiate its power out, because of its temperature, it's radiating the power out. What actually happens is that energy gets absorbed by the atmosphere, and some of it, not all of it, actually gets reflected back to the Earth. So you have some energy trying to go out, it gets absorbed by the atmosphere, and the atmosphere absorbs that light and then re-emits it randomly. Well, when it re-emits it randomly, it re-emits it in all directions. But notice that a bunch of those directions actually end up going back to the Earth. And so what's happening is that power output that we thought, where is it here? That this power output is actually not that there's actually the Earth is able to retain, that's actually less. So like there's actually a little bit less going out than we thought it would. And then that's actually causing the Earth temperature to be a little bit, the Earth average temperature, the balance, because there is a temperature balance. The Earth's temperature, we want it to be constant. And so what's nice is there's this thing called the greenhouse effect. And the greenhouse effect says that we actually end up losing a little bit less energy than we think because it's being absorbed by the atmosphere. Questions? Lesson next time is going to be all about this idea that the Earth is trying to radiate energy out. Then the Earth's atmosphere acts like a blanket and it sort of retains that heat. So it says that not all the heat can actually escape to space, that some of that energy gets reflected back down to the Earth. And then that ends up raising the Earth's average temperature. So it upsets this energy balance. Now, this is a good thing, right? Without the greenhouse gases in our atmosphere, there would be no life on this planet because the average temperature would be -7 degrees Celsius. But because we have an atmosphere, it is able to raise up the temperature a little bit. Like we're able to do this a little bit more, and then reach a constant. But that's the idea. Cool. That's it, guys. So I'll see you on Thursday. Have a great rest. Or is it Thursday? Wednesday. I'll see you on Wednesday. Have a great rest of your day. Bye.